Okay, I'm going to start my second session on the discussion of regression equation. So you can see the Excel sheet which I'm presenting you right now. In this Excel sheet, I have calculated I have taken a bivariate distribution of the following form. This bivariate distribution is having the value, having two variables. One is the response variable y and another is the input variable x. And this the number of pairs present in this bivariate distribution is actually 4. For simplicity, I am taking this. Okay. Also, the correlation coefficient of this bivariate distribution has also been found, and it is noted here as 0.989476. This is the correlation coefficient between the two variables, capital X and capital Y. I told you in my last class how to find the regression equation with the help of Excel. If you have not, if you can't remember this, you can see my morning session video. There also I showed the students how to do it with the help of Excel. So that will be a quick recapitulation of the thing. I'm not going to repeat that thing here because it has already been discussed. So the regression equation, as you can see, it is obtained as follows. I'm writing it clearly. The regression equation that has been obtained here is y is equal to 1.914 x plus 2.485. This is the regression equation that has been obtained. And we can see that since it is the line of best fit, this regression equation is the line of best fit. Since there are 4 points, only 3 points, majority of the points are actually falling on the straight line. Only 1 point is there, which is a little bit of deviated from the line. Okay. So it is not actually a problem. Now, suppose any student, if suppose he has not found the straight line equation, he just want to estimate it by visual inspection. One particular student do it in this particular manner, isn't it? That will be a kind of straight line also. Now, if he does so, if he draw the straight line in this following manner, he will see that this is also a straight line that I can assume for some values of the parameters alpha and beta, because since the parameters alpha and beta are not known, they has to be estimated. Now, suppose we do not know how to find the line of best fit. Suppose the method of least square is not known. We have assumed certain values of alpha and beta, and for this value, I am getting this straight line, which marked as green color. If someone does so, what will happen then? He will find that the deviation of this point will be maximum from the line. Not only this, the deviation of this point will also be maximum. The deviation of this point will also be maximum from the line. So here the deviations are pretty maximum, pretty high deviation. But since we know the technicality of the line of best fit, we have got this particular equation where we see that there is a very small deviation for this point with respect to this line. Otherwise, most of the points are falling on the line. So therefore, the regression equation is called the line of best fit. Now, one interesting part that you can observe in this particular case is the following. See, with the help of Excel, I have also calculated with the average of the variable input variable x and the average of the response variable y. These averages have also been calculated. So I am highlighting these points over here. These averages has also been calculated. You now try to you now carefully observe one thing which is pretty interesting, and it actually is aligned with our theoretical knowledge, that you can check that if I substitute the value of x to be 2.75, and if I do the calculation, let's see what comes out of it. 1.914 multiplied by 2.75 plus 2.485 will give you 7.7485. And you know that in this particular case, we have chosen this value 2.75 is nothing but x bar, and the value that has been obtained is equal to y bar. Okay. So why is it happening? By putting the value of x bar in the equation, in the regression equation, we are getting the value of y bar, average of y bar also. It is because during the process of finding the regression equation, we have come across an equation of the form y bar equal to a plus b x bar. So the average of these, if you are able to find the line of best fit, if you are able to find the line of best fit, then this will always be the case that the average of the response variable and average of the input variable will pass through that line. This is a very interesting fact. Try to recall another interesting aspect from our discussion on the derivation of line of regression. What is that thing that I want to tell about? We deduced two equations which were known as normal equations. If you can remember, what was my line that I considered? My line was like this: yi equal to a plus b xi. That was my line. Okay, and with respect to this line, my normal equation were summation yi n into a plus b summation xi and summation xi yi a summation xi plus b summation xi square. These were termed as normal equations. Okay, I don't want to get into the line of best fit now. What I want to do, just for checking, that if we consider these normal equations only, do I get the line of best fit? So for that, what I have done over here is this equation, this normal equation needs the summation of the response variable, the summation of the input variables, the summation of the product of response and input variable, and the square of the input variable. These quantities are required. If I can get hold of these quantities, all these quantities will be substituted in the equation. And in this case, we get two equations in terms of capital A and capital B. And then this pair of equation can be solved for capital A and capital B. So by keeping this in mind, I have formed a table over here. As you can see, I have retained the variables of x, the values of x, just as it is given in the question. The values of y is retained just as it is given in the question. I have calculated xy, I have calculated x square, and all these figures shown over here are the summation, sum of these columns. Then I did it. I am not going to repeat this process, but if you want to, you can do it by yourself in your copy. I substituted all these values in the equation. Okay, I'm just giving you the values. I'm just showing you after substitution how does the value look like. So for the first normal equation, what we have summation yi. Summation yi is 31. I have to choose a dark color. Summation yi is 31. How many variables are there? 4 variables, 4 pairs are there. So 4a plus b summation xi. So that will be 10b. And for the second equation, we will get summation xi yi, which is 90, is equal to a summation xi, that is 10a, plus b summation x square, that is 30b. Now you can solve this equation for a and b. You will find that equation will be of the form, if you solve it, it will be of the form this 1.5 plus 2.5x. Our line of best fit was this 1.914x plus 2.485. And we have got another equation through our knowledge of normal equation, that is y equal to 1.5 plus 2.5 into x. Obviously, these two equations are different from one another. And we will also observe that if you substitute the average value of x in this equation, the average value of y will not be obtained. Okay, so this equation, although can be found, is an equation, but it is not a regression equation. It is not a line of best fit. Okay, so with the help of this example, I am trying to tell you that you can fit various equations to the set of variables, but not every equation is the line of best fit. But a line of best fit is definitely a line of equation. Okay, I'm stopping the share of this Excel file, and I'm going to the whiteboard section. If you look at your syllabus for the time being, you will find that there is a unit 5 in which the unit 5 starts with the topic of curve fitting. Curve fitting is a topic where the values of the response variable and input variable are given. And by looking at the scatter diagram, you have to fit the best possible curve that is satisfied by all the points. Okay, in the curve fitting section, there is one fitting which is called the linear fit. Curve fitting, linear equation, or sometimes we call it as linear fit. So when the variables are given, then we assume a straight line equation, yi equal to a plus b xi, and with the help of normal equations of the form yi summation yi is equal to na plus b summation xi, summation xi yi, a summation xi plus b summation xi square. We try to fit the straight line equation to the given set of data. Sometimes some authors does this kind of thing also. This is a kind of process which is sometimes applied. If I am not interested about the line of best fit, we can also go for this particular process. It is often used for business forecasting or weather forecasting. So this process is called the linear fit under the section of curve fitting. And you can say that this section of unit 5 is pretty much related to the regression equation. And you can consider that has been discussed. So when I'll start unit 5 later on, I'm not going to discuss this linear fit with respect to the normal equation once again. I am trying to show you the line of best fit and just a straight line, which is not a best fit, together, so that you can identify the difference between them. Okay. So I hope the message that I want to convey to you is clear. So if you have any doubt, you can later ask me regarding this particular chapter, because this chapter is, you can see this, it is not a very easy chapter to deal with. People think that it is a very easy chapter, but it is not like that. There is a scope of more analysis over here. You have to analyze the situation before you come into a particular decision. Okay. Anyways, so I have shown here I have shown you how to find the line of best fit by using the method of least square. Let us try to solve a problem on the basis of this regression analysis. In a particular, in a partially destroyed laboratory, record of an analysis of correlation data, the following results are only legible. Okay. The data which can be retrieved from this partially destroyed laboratory are as follows. Variance of X is 9. Regression equations are given to be 8x minus 10y plus 66 is equal to 0, and 40x minus 18y is equal to 214. Now the question is, if this much data is retrieved from the partially destroyed laboratory, what are the mean value of X and Y? Number 2, the correlation coefficient between X and Y. Number 3, the standard deviation of Y. So from this information that is given, can I retrieve the following 1, 2, and 3? That we need to find out. Okay. So to solve this problem, first of all, you have to, know only one fact, and it is that the mean values of X and Y, that means this and this, X bar and Y bar, they should satisfy the line of best fit. It happens with the regression equation of Y on X. It also should happen with the regression equation of X on Y. Because if you have the regression equation of Y on X as Y equal to A plus BX, this needs to be true. Not only that, if you have the regression equation as X equal to A prime plus B prime into Y, then this also has to be satisfied. That much information we know. So to start with, we are writing that since both lines of regression pass through the point x bar comma y bar, we have two equations. One equation is 8x bar minus 10y bar plus 66 is equal to 0, and 40x bar minus 18y bar plus is equal to 214. We have these two equations. I am asking all of you to take some time and try to find out the value of x bar from here and the value of y bar from here. So I'm waiting for your reply. Once you do it, you write it in the chat box, and then I'm going to continue with this particular problem. So these are the values that you have calculated. The mean of x is 13 and mean of y is 17. Now you see the first part of the problem is done. Yeah, somebody else, Nasal, has also got 13 and 17. This time both of them are their results are matching. So first part of the problem is done. You see, we have got from the given information, we are able to find out the mean of x bar and mean of y bar, mean x bar and mean y bar. Our next job is to calculate the correlation coefficient between rxy, correlation coefficient between x and y. Information given is that there are two regression equations. One regression equation is this, and another regression equation is that. But what we do not know is the following. We do not know which regression equation is y on x and which regression equation is x on y. So what you are going to do now is that for problem number 2, we are going to assume according to our choice, and we are going to call one of the equations to be regression equation of y on x and another equation to be regression equation of x on y. So we consider let 8x minus 10y plus 66 equal to 0 be regression equation of y on x, and let 40x minus 18y is equal to 214 be the regression equation of x on y. So these two regression equations now can be written in the following manner. So from the equation y on x, we can rewrite this in the following manner. Since we are assuming that it is regression equation of y on x, so we will try to keep y on the left hand side and we'll try to bring everything on the right hand side. Similarly, since we are assuming this to be regression equation of x on y, we will keep, because it is our usual notation, we will try to keep x on the left hand side and we'll take everything to the right hand side. So if I do so, if I keep y on the left hand side and take everything on the right hand side, what we get? We get minus 10y equal to minus 8x minus 66. And y will be minus 8x minus 66 by minus 10. So which is equal to 8x plus 66 by 10. Or more specifically, it is 66 by 10 plus 8 by 10 into x. So this is my regression equation of y on x. Similarly, from x on y, what do we get? We are going to do the same thing over there. So we get 40x is equal to 214 plus 18y. So we get 40x is equal to 214 plus 18y. 18y. Okay. So this implies that x is equal to 18 by 40. Or first of all, let me write this part. 214 by 40 plus 18 by 40 into y. So we have got two equations of this form. We have got two equations of this form. And once we write this equation in the following manner, we already know that our regression equation is y equal to a plus bx. Our regression equation x on y is x equal to a prime plus b prime y. So we get our regression coefficient capital B, which we generally call denote by byx. It becomes 66 by 10, and b prime, which we generally denote by bxy, it is becoming 214 by 40. Okay, so we have got our values. No, sorry, one thing. This is not the regression coefficient. Regression coefficients are this one. B is the coefficient of x. Sorry, coefficient of x is the regression coefficient. So the first regression coefficient will be 8 by 10, and the second regression coefficient is 18 by 40. Okay, now it is all right. One is 8 by 10 and another is 18 by 40. And we know from the property that we discussed in our previous class that correlation coefficient squared is actually the product of the two regression coefficients. So we can multiply these regression coefficients together, and then we can take the square root of that, which will be plus minus 8 into 18 by 10 into 40. So let me calculate and let me see what comes out of it. So 18 into 18 by 400, the correlation coefficient is coming to be plus minus 0.6. So you see, actually two possibilities are coming. Two possibilities are coming. One possibility is that the correlation between the two variable capital X and capital Y is either 0.6 or it is minus 0.6. So if Rxy is 0.6, at least we know that X and Y are moving in the same direction. This much we know from this information. If Rxy is equal to minus 0.6, that means X is moving in the opposite direction to that of Y. Okay, but here we are not sure about which one is correct. Either the two variables are moving in the same direction or they are moving in the opposite direction, because two possibilities has emerged. But a little bit of analysis will help you in this regard. We see that the two regression coefficients obtained from the equations, regression equations, are indeed positive, isn't it? They are positive. because one regression coefficient is 8 by 10, another regression coefficient is 18 by 40. So they are positive. This implies that their product will be positive. This means R square is positive. This means R should be taken to be positive. I shouldn't write R is positive, because if the product is positive, if the square is positive, then the value can be negative or positive. But since we are talking about the correlation coefficient, something else is happening over there. So the two regression coefficients, since the two regression coefficients are positive, so the correlation coefficient between them has to be taken to be positive always. R must be positive. So we can consider that we can say that the two variables are actually moving in the same direction. There is a theorem actually where it says that you can try to find this out with I have not done this property in my last class, that the nature of the correlation coefficient is actually dependent on the nature of the two regression coefficients. Okay, so what will the sign that the correlation coefficient will carry inside it is dependent upon the sign that will be carried by the two regression coefficients. Okay, if the two regression coefficients are negative, okay, then also the correlation coefficient will be positive. But if one regression coefficient is positive and another is negative, then that is a problem. So we can say that the correlation coefficient is this one, 0.6. So second part of the problem is also done. The third part of the problem, the last one, is to find sigma y. Now we know that byx is given by the relation rxy by sigma y, rxy into sigma y by sigma x. We have already found the quantity rxy, which is 0.6, and sigma x is known. Sigma x square, the variance of x square was given to be 9. So this implies that sigma x is 3. So we can put it over here. Sigma is positive, so we are considering the positive square root only. And byx is actually having the value 8 by 10, that is 4 by 5. So in place of byx, we can write 4 by 5. Now, rest is a very simple calculation. You can find sigma y from there. So sigma y is coming out to be 4. So in this manner, you can calculate with the help of regression equation various other things which are essential for studying the bivariate distribution. So, but always remember, and there are many other problems which you can try to do by yourself. Not all the problems, it is not possible to show you the solution of all the problems, but if you are stuck in a certain problem, then you can anytime knock me and you can write it in the WhatsApp group, or you can ask me, you can call me directly. So you have to do the problems by yourself, otherwise you will not be stuck, otherwise the doubts will not be cleared. I'll suggest you try to solve as many problems as you can from the chapter of correlation and regression, because it has some sort of direct connection with engineering studies, higher engineering studies, and the analysis is not very easy. It's kind of a complicated analysis. The way I have presented it, remember that only a fraction of these things have been discussed with you. Not everything has been discussed. Lots of other questions are there which can only be whose answers can only be found if you solve the exercise. Okay, so try to do as many exercises as you can, as many problems, short problems as you can on this regression analysis, and try to clear your doubts. Go through my videos, which has already been uploaded in the YouTube. Start from the first video on correlation and come up to this point. Okay, go through all the videos at a time. Okay, not sporadically. And because if you choose the videos arbitrarily, say suppose you are only seeing the regression video, maybe some information are there which has already been discussed in the previous video, then maybe you will be in trouble. You will not be able to understand, you will not be able to grasp the point. So every video of correlation and regression is actually interconnected. Subsequent videos are dependent on their previous counterparts. So go to the video once again in its entirety and try to clear your doubts in a better way. Okay, with this, I'm going to conclude my today's session. We are again going to meet next week with a new topic. Till then, bye.